Yeah, it's like I was saying, it's great to be here after 50 years, and I just find it wonderful here in Israel, and everyone is so Israeli. Yeah. What can I say? It's great. So I'd like to speak to you about something that I think is extremely important, and that is the future of the digital world. And I think that WeChat, of all things, has proven unequivocally, without a doubt, that the killer app is messaging combined with payments. And if the blockchain is going to survive, it needs to try to provide a better WeChat. That's my strong belief. And that means WeChat with a new level of privacy, and I think that this is possible, and I'd like to show you in detail here a bit about how we can achieve that. So I think, yeah. So that's the real challenge, taking blockchain mainstream. That will ameliorate all of our regulatory issues, and that will allow this technology to reach its true potential. So in order to do that, there are really 4 key requirements. The first is naturally speed. We have to be able to do consumer transactions at the kinds of speeds that consumers expect. 10 seconds, payments, and messaging, from initiation to finality. We need a level of privacy. Now, some think that privacy is optional in cyberspace. That's not the case. For consumers, there must be a basic level of privacy. No ordinary person wants all of their payments and messaging public on a blockchain immutably, transparently, in perpetuity. That's not acceptable. We need a basic level of privacy at least, and if you think about privacy, you might think of a vertical level, which is the unlinking of the user identity, which is maybe IP address or phone MAC address, to the transaction, and then also the horizontal unlinking from transaction to transaction. And both types are needed. In messaging today, we don't have this, in fact. Remember, Snowden told us about the full take. So if we can offer this kind of messaging. Oh, okay, I can use this. Yeah, thanks very much. Okay. In messaging, then that would be unprecedented, in fact. Current messaging systems only offer so-called strong encryption of end-to-end privacy of message content based on elliptic curves. And this probably isn't adequate. It has nothing to do with protecting the metadata, the social graph, who talks to who and when, and so forth. This is what the public is now starting to realize is critical in order to take back our informational lives. So once we are able to offer these kind of facilities, then they will come, and we need scale to be able to address this user population of maybe hundreds of thousands of people who are in our community right now, and ultimately millions of transactions a second, and that's simply what's needed. And finally, there's a requirement that you don't hear about generally, and that is that the level of security that we have today in these systems is not really secure against national adversaries. And, you know, when I say quantum resistant, many people assume that I mean cryptography that will, if quantum computers become real, will resist them. But there's another meaning for quantum resistance, which is that these are codes that are not predicated on mathematics that has very strong structure in it. So, in fact, if you have worked in military or high-end industrial security, you know that it's much better to base a code on a random function than something that has a lot of structure. So I personally don't believe that governments in medium-sized countries would be willing to allow their whole consumer payment system and messaging system to be attacked by another country that could break, say, some elliptic curve. That probably is an unacceptable threat. You could, for instance, learn a tremendous amount about the economic activity, compete unfairly. You could disrupt the whole economy, which is something that's done in time of war, as you may know. You could target particular individuals and terrorize society. There's a lot of things that could be done. You don't create what actually is wanted is a level playing field for the new kinds of financial services that emerging countries would love to offer to their citizens, but they don't want a kind of economic imperialism. They'd like to be able to offer those services nationally as well as be able to take advantage of international offerings. So the kind of security that is needed is something that is not really been achieved to date. It has to be based on a quantum-resistant cryptography. So if we can do that, then we will have, if we can meet all four of these requirements, an infrastructure that will allow people to have a protected space where they can freely communicate and also pay for information without any fear of retribution, and have an open economic system that will allow everyone to benefit from all the sophisticated products and financial services and so forth, and ultimately provide a great platform for dApps, which will help create an hard to imagine but far better digital world. So we in the blockchain community have known for a long time that this is what's needed, at least in terms of payments. Messaging has been largely left out, but everyone's been trying to get there, and there's a lot of, promises, but I'm afraid no one's getting anywhere near close to being able to do this. So that's why I kind of came back, and we have found a way to actually achieve all four of these properties, and it wasn't really possible with existing techniques. That's why, in my view, no one's been able to achieve these. We needed some real fundamental breakthroughs. So it took me a lot of effort, but I found a new way to do mixing, which was mentioned in the intro here, something that I proposed 35 years ago, and no one really seemed to have found a way to speed up yet. So I put some effort into it, and I found a way to speed it up by about 1,000-fold to make it now possible to use it for chat messages from smartphone to smartphone. And the implication for that, for the blockchain, is that instead of a single node producing each block, we have a team of nodes, 8 nodes, for instance, that produce each block. Now, those nodes are selected by a distributed randomized algorithm so that each block is produced by a different set of 8, but they do know in advance when they will when their time will come up, more or less. And so the trick is they're able to do a computation in advance so that when their time is up to be the 8 nodes to produce a block, they can do things very efficiently. And I'm going to explain that to you here briefly using an analogy with these silly cartoons. So suppose that Alice wants to send a message to Bob, but she doesn't want anyone to know that she's in communication with Bob. This is the metadata problem, the traffic analysis problem, the problem of protecting the social graph. You can secure the message content, maybe, but without protecting the whole traffic analysis, you really are missing the ability to take back control over your informational life. And in fact, if you can't solve the traffic analysis problem, maybe you haven't actually solved the man-in-the-middle problem. And probably all of your, much celebrated strong end-to-end encryption is a joke because there can be a man in the middle. So how do we do this? Well, the example shown here is 3 robots that are representing 3 nodes in the blockchain. Really, there'd be about 8 of them. So each one of them is doing a lot of heavy work in advance. They each choose their own independent secret key, and they use that key to determine a rearrangement of these pipes, a permutation, if you will, a random shuffling from the input to the output of that box of theirs. And so each one of these is independent. They seal those boxes up, and this takes them a lot of work, and they're doing this in advance so that for that 1 second when their team is active, that whole batch of messages that comes in on the upper left there, let's see if this pointer is at all visible. No. No one can tell which tube, Alice is sending her message in, it comes out from. I wish I could, I guess this mic is still not working. Oh, well. This one's working now? Oh, hey, look at that. So, hey, this is great. So when Alice puts her message to Bob in the tube, then it gets shuffled through these things like the Hyperloop, just flies through. Each one of these permutes it randomly, and so when it comes out here, it can be delivered to Bob, and then actually the robots can then stuff a little blue check mark in there, which will come back out, and Alice will get it, but they won't know still who Alice is, and then these boxes will be destroyed because we don't want to reuse them. So all that work to build all this plumbing results in a very fast transfer of messages, but in such a way that unless all the nodes collude, no one can know who sent which message to whom. So that's the way we deliver messages, and later we can also do payments through this. So let's talk about payments for a minute. That's the other thing we need to do the WeChat functionality. Well, current blockchains use elliptic curve signatures to create what are like digital checks. It's a signed thing saying move money from my account to somebody else's account. This is a very traceable, horizontally mechanism, not suitable, and because it doesn't have quantum resistant security. And it's also kind of linkable. So what we do in Elixxir is we reinvented payments for blockchain, and we've drawn on the technique that was used by DigiCash in the 90s in the eCash product, which, how many people know that eCash was issued as its own currency in an airdrop in the 90s called Cyberbucks? So go to my website, chaum.com, you can see all the different shops that were accepting it and so on. And also it was issued by Deutsche Bank and in Deutschmarks and US dollars and Australian dollars and so on and so forth. The way all that eCash worked was with fixed denominations. They were binary denominations, just like coins and paper money. So each payment was made up of a collection of fixed denomination digital bearer instruments, numbers that were worth money. And those digital bearer instruments were digitally signed, so once you received one through the blind signature process, no one knew which one you had, and so no one could take your money away from you, and you could spend it at any time, and no one would know who had withdrawn that money. Here, we cannot use public key digital signatures, so we use hash functions to validate these bearer instruments, but they are still binary denominated, just like eCash was. And so let me show you, again with a silly cartoon, an example of a doubly very simplified version of how we can do payments simply using hash functions. So when Bob wants to receive $1, so we're just doing a single denomination, from Alice, he creates a secret key, a random key, that's shown as this combination lock, and then he hashes that key to create what's shown as a box, and he gives that to Alice. So if Alice decides to pay Bob, then she sends 2 numbers in as a message. Now let me just remind you that those could be sent in here, and no one can tell whether Alice is sending a text message or a payment. If it's a payment, it's not addressed to Bob, it's addressed to the robots. And so they will cooperate to make this payment for Alice. So she sends the hash that she got from Bob, of course, and the other number she sends is the secret key that she created when she got the $1 in the first place from Joe. So she got this dollar coin somewhere, and for that, she had to create a key, and then she hashed it. And that key is what she sends in. So the nodes can all hash that secret, see that that hash is on the Patricia tree, and then they burn it and move the value to Bob's box, which is then placed on the tree, and now everyone can, using their block explorer, look and see that Bob's hash is on the tree, and so now he knows that only he can spend that money, and there's finality. But actually, it's much better than this, because if you remember, we have a way to send those messages back through the return path, the little blue check marks. So we can actually send a Merkle signature of this node this hash back to Alice as a receipt for finality, and she can check that a quantum-resistant proof of finality is now received by the payer, and of course then she can send that to Bob, and then Bob gets it, and he has this quantum-resistant proof of finality, and no one's burning up a lot of network traffic or anything. These are just like a couple thousand bit messages traveling through the system. The more messages, the better the anonymity, the better the privacy. That's a funny thing about these networks. We like message traffic. So we've actually built this stuff, and it's been running for a number of months. We have automatic deployment using Terraform and Docker on all kinds of cloud services, and this is just an example showing 3 different clouds, and then these are the server logs on those clouds. This is our Block Explorer, which is public. These are messaging clients that work in a really funky, old-fashioned way, which is a cursor addressable console interface. We've been using that, so that runs on all the workstation platforms, and so we've been using this internally in the developers for months. This is all great, and then we also have the payment system implemented in a similar way, and it's tested and everything like that. But the really interesting thing is those same APIs which support the console-based UIs, which we've been able to perfect because we didn't spend a lot of time on the GUI, now we can run those on iOS and Android. And they are running, and we have like beautiful UIs, which I guess I'm not going to show you yet because we haven't revealed them, but they're looking very good. And there's also, the interesting thing is that the amount of time the user has to wait, the amount of network bandwidth used, or data plan, if you will, the amount of battery on the mobile platform, the amount of processing time, those are all comparable to other messaging apps and so on. So we have like benchmarked all this and so forth, and I look forward to showing you that this is pretty well documented. And here's something new that I'm going to show you here for the first time, and that is that we've looked at allowing the user interface for messaging to conveniently be adapted to make payments using other types of cryptocurrencies. And so we can, in fact, accommodate the various types of Bitcoin. So now what am I saying here? Is this some kind of system where we require a third party to be trusted? No. We're just allowing the private messaging of Elixxir to transfer your Bitcoin payment to a gateway, and so that it can be promulgated on the network. And similarly, when your transaction does appear in a block, then we'll notify you through an Elixxir message. And then after half a dozen additional blocks, we'll notify you again that it's really pretty safe. And so we can do that for all the various types of currencies here. It's not, please don't misunderstand us. We're not saying we don't like these ones or we don't want to use them. Some currencies have happily, and in the documentation it says no one knows why it's there, but put Merkle trees in the blocks. Well, that's great because that allows us to send the confirmations and so on in an economical way. We have to cram everything into 4K bits. That's you know, when you want to have a private messaging system, you can't be like like Brand X, where they say, oh, send any message length you want. I mean, they're insulting your intelligence with that stuff, right? That's a pot if I ever. So you have to have a fixed block size, just like I said in my original mixing paper from 82. So we have to be able to fit the requests and also the Merkle signatures showing that your transaction really got through. We have to be able to fit it in there. And so those messages are indistinguishable from text messages and everything else. So it's a beautiful thing. More traffic, more privacy. So we would like your help in realizing all this if you find this interesting. And now I'd like to talk very briefly about dApps and smart contracts, and we're honored to have Nick here, and it was great to have Nick working at DigiCash for half a year back in the day. You can see his picture on my website, happily as part of the team there on the far right. But you know, any smart contract or dApp can be divided into two parts conceptually. There's the business logic, which is sort of the everything else. You might think of it as a multi-party computation. And then there's the multi-sig part, which is what allows it to interface to the Elixxir chain. So in other words, we can run any smart contract or dApp off-chain with minimal slowing of the chain itself. In fact, we have such an efficient multi-sig mechanism that it's only a few percent less efficient than just a single signature. So we can allow the dApps to control everything they do, like messaging and payments, through multi-sig, and then they will appear to the user as if they're running on-chain, which is what you have like with WeChat, especially like in China. You know, there's apps that seem to be running within WeChat. That's the way these dApps will run. They're in your environment, yet they don't slow the chain down whatsoever. And it makes a lot of sense because different dApps may need different kinds of computing environments, different trade-offs in terms of censorship resistance, immutability, computing power, and that sort of thing. So we create a marketplace for these dApp engines and so forth, which I'm not going to go into here, but that's an exciting thing about when you can make a consumer messaging and payment system, then you provide the ideal platform for dApps. So, thank you very much.